Welcome to the 8th video of our Checkpoint Labs. In this video we will discuss CoreXL, and for the lab activity we will reconfigure the default CoreXL settings for the setup with 4 CPU cores to 50-50 split between security network dispatcher and firewall instances. CoreXL is one of the most important checkpoint features because it allows you to manually tune performance of CPU through management of the CPU cores. You can configure how many CPU cores can be used by security network dispatcher and how many CPU cores can be used by firewall worker instances. Also, you can manually configure some checkpoint processes to be locked to one or many CPU cores. Why we even need CoreXL? CoreXL is needed because if we do FWDIR affinity, we will see that some interfaces can take CPU time from any CPU, and at the same time each firewall worker can take CPU time only from certain CPU cores. In low volume of traffic, this is not a problem, but in case if we will have more and more traffic, it may cause a problem. For example, Ethernet 1 can occupy CPU time from CPU 1, and the CPU 1 can also work on traffic processing through policy and performing some inspections. And meanwhile, CPU 1 is occupied by firewall worker. A packet in the RX buffer of Ethernet 2 will wait until CPU time is free. At some point, it may lead to a packet drop on an interface. The other scenario is, for example, if FWDIR have to send a lot of logging and it can occupy the same CPU cores which are assigned for firewall workers. It may occupy, let's say, CPU 3. CPU 3 can be busy by a firewall worker 0. In this case, firewall D will have to wait until CPU is free to use. And if at the same time FWDIR will be first to occupy CPU number 2, firewall worker 1 will have to wait until CPU number 2 is free from FWDIR processing, and meanwhile the traffic will wait until firewall worker finishes the rule-based inspection or some other security evaluations. And this in turn will lead to some interfaces waiting for the traffic to be processed by firewall worker, and SND will wait because it may have no option to distribute this traffic because all other firewall workers are equally busy and the buffer of each firewall worker is already full. CoreXL in default after configuration may be optimal for easy conditions, but the more traffic volume we have to process, the more firewall features we have enabled, the better will be to configure the CPU assignment manually rather than trusting into CoreXL after feature. How can we check what is the CoreXL configuration? CoreXL by default has 3 firewall instances for kernel and 1 firewall instance for security network dispatcher, and that's exactly the case which we have on our web firewalls because we have exactly 4 CPU cores. Let's review the process in a little bit more details. Let's say we have some traffic arriving on the RX buffer of an interface. For this example, let's say we will have interface 0, and this means that that's most probably some management traffic. To process the packet first, this packet will have to go to security network dispatcher, because let's say that's the SYN packet. This packet will arrive on SND, and SND will have to assign some of the firewall workers to process this packet for the rule base. Let's say SND selected firewall worker 0. We can double check. Okay, firewall worker 0 is sitting on CPU number 3. Means this CPU After the rule-based processing, firewall worker 0 will return this packet back to SND, and SND will send this packet to TX buffer of some other interface. Let's say this is some packet for smart management server. Smart management server is behind Ethernet number 1, Ethernet 1. And then this packet go to SMS. And here is admin laptop. Okay, for each of these steps, we will need some CPU time. First, SND will spend some CPU time to get this information from RX buffer and then distribute this information to one of the firewall instances. We see that SND can occupy any CPU core. For Ethernet 0, it is also any CPU core. Let's imagine that for some reason it took time from CPU number 3. CPU number 3. When it is trying to distribute it, selected firewall worker number 0, it also uses CPU number 3, and this traffic will be worked through firewall policy. At this moment, CPU number 3 is busy, and SND cannot occupy the CPU anymore. Even if it has many packets and all other CPUs are busy, this firewall worker already occupies CPU 3 and cannot, SND will not be able to occupy the same time from the same CPU, and you have to wait. If SND will wait too long to take this CPU core, which is busy, some of the oldest packets at some point will be dropped from the RX queue because it was sitting in the RX queue for too long. And we will see this counter on a firewall as RX miss drops. For example, if we do ETH2 minus S Ethernet 0, grep drop, grep error, we will have RX miss errors. So every time when the situation happens like described here, we will see increase of RX miss errors. Then when traffic is processed by firewall worker, it will return to SND, and SND can occupy any other core. Say it will be CPU number 1. But CPU number 1 also can be used by a firewall worker, so in case if CPU 1 is already occupied, then SND will have to wait, and it will cause also some delays for packet processing in the future. And only after that, the traffic will arrive to the TX queue of the Ethernet 1, and then it will go to the destination. That's the main problem with the automatic CoreXL affinities, is that sometimes tasks on the CPU cores may overlap. CPU cannot handle two separate tasks at the exact same time because CPU time can be booked by only one process at the same time. And the main reason why we want to have manual interface affinities is because we don't want SND tasks to overlap with firewall worker tasks or to overlap with some other checkpoint process. So what we will do for our lab, we will reconfigure CoreXL for the lab. So the SND will be able to occupy only CPU 0 and CPU 1. And the firewall workers will be able to occupy only CPU 2 and CPU 3. For this, we will implement a 50-50 scenario when first two firewall cores will be assigned only to SND, and the second two firewall cores will be assigned only to firewall workers. To do that, we will need to open our firewalls. Let's open the second session to gateway number 2. And let's put it side by side like this. First thing to remember is that when we change a number of firewall instances on the firewall, this will be a mismatch between two cluster members. And firewalls cannot be in the same cluster when they have different number of firewall instances. And during the time of the change, the synchronization between our firewalls will be paused, and cphaprob start will show that one of the firewalls is not available in the cluster. Let's start with the checking current cluster status. We see that local firewall is active, gateway number 1 is active, and gateway number 2 is standby. Then we will use cpconfig to configure checkpoint CoreXL. It's option number 9. Then we need to change the number of firewall instances, and it's worth mentioning that to find out how many SND instances we have, we just take number of CPU cores and then subtract the number of firewall instances. Basically means that we will select 2 firewall instances. 4 minus 2 will give us 2 SND instances. So we will put number 1 as an option, and we will put 2 CPU cores for firewall instances. And to apply this configuration, we need to reboot. If we do cphaprob state now, still we have active standby, no problem. Time to reboot. Gateway number 2 is back from reboot. We can log in. The first thing to check is cphaprob state, and we see that the local is down, the other one is active. Here we will do the same, cphaprob state, and we see that the local is active, the other one is down. So it means that if we have any packet going through the firewall cluster, then it should arrive on WAP gateway number 2. In this condition, when we have firewall number 1 is down and the firewall number 2 is active with a problem, we can do some experiments. For example, let's try to establish a TCP connection through the firewall cluster and see if connection will still be synchronized even if we have this cluster as down active. We can, before doing the test, we can check cphaprob sync stat. Sync stat, and it shows that sync status is okay. If we do the same problem, the same command here, we also see that sync status is okay. Now we can do a fwctl con tab minus source IP equal 192.168.43.1 and destination IP equal to 172.16.100, and it shows that we don't have connections right now. Same command on the other firewall member shown same. Okay, and let's do watch -1 minus D, the command, and here as well watch -1 minus D, and then the command. No connections. If we do SSH session, we see that the connection was successfully synchronized, and we have connection on both cluster members. But the traffic indeed goes first through the WAP gateway number 2. Let's double check this with the TCP dump. TCP dump for interface Ethernet 0, ICMP traffic only. The same we will check on the second firewall. And now we will try to ping WebSMS. And we see the ping going now through the gateway number 2. FWCTL affinity show that we have a firewall 0 and firewall 1 on CPU number 2 and CPU number 3. Still, we don't have any manual interface affinity. That's why any interface can take any CPU. To fix this, we will need to create a manual interface affinities to only CPU 0 and CPU 1. Before doing this, let's bring this cluster to normal state, active standby. For this, we will need to reconfigure CoreXL on gateway number 1. Select number 9, select number 1. We need just 2 CPU cores. And then we can exit again to apply the changes with reboot. We see that firewall number 1 now is back from reboot. We can log in and we can check the cluster status. Now it is active standby, and again active standby. This is the normal state of the cluster. We preserve for the current active firewall. We do not fail over back immediately to the cluster member with the high priority. The high priority cluster member has ID number 1, so now it is standby, and active is the web gateway number 2. If we do FWCTL affinity, we see that the configuration now is the same between two cluster members. Okay. To check what's going on with interface affinity, there is another command. It is sim affinity -L, and we see all CPUs for each interface. Same command here. Show the same result. All CPUs for all interfaces. Now we can configure manual interface affinities. Let's start with the standby firewall. Standby is now gateway number 1. To configure manual CPU affinities, we use command sim affinity -S. And here we can specify which CPU core we want to be used by each interface. And in the brackets, we see the current configuration of this interface. Right now, Ethernet 0 can occupy any core. We know that Ethernet 0 is not the busiest of our interfaces. It is required only for management traffic. And we know that CPU number 1 Ethernet number 1 is used for the external traffic, and Ethernet number 2 is used for sync traffic. Generally, it's a bad idea to share sync interface with any other interface on the firewall, because sync interface usually send more traffic the more traffic we receive on any other interfaces. And if we will merge the sync interface with any other interface for CPU utilization, the more traffic we get on the interface, the more traffic we generate on the sync interface, and this works like a snowball basically. So we don't want to do that. That's why we will use CPU 0 for Ethernet 0 and Ethernet 1, and we will assign a separate CPU core for the sync interface. So here we will use 0, here we will use 0, and for the sync we will use 1. Now we can check the current status of the sim affinity, and we see now it is 001. If we do FWCTL affinity, Now we see that 0 and 1 goes to CPU 0, Ethernet number 2 goes to CPU 1, and firewall workers use CPU 3 and CPU number 2. Also, we can notice that all the other firewall processes automatically share only CPU 2 and CPU 3. Firewall processes will not go to the SND CPU cores. This change to be applied does not require any reboot. It is effective immediately. To roll back the change, we can go sim affinity -a to bring it back to the default configuration. So let's try to do that. So nothing basically changed. So after means it respects the configuration which we configured manually. Actually didn't change anything in interface affinity and didn't change anything here. Just to be sure, I will repeat the steps. We'll assign 0 to Ethernet 0, 0 to Ethernet 1, CPU number 1 to Ethernet 2, and that's it. Okay. Okay. Oh, good. We can do another experiment. We didn't change anything in affinity.conf file, and still we will try to reboot the firewall and see if the settings are preserved. To check what's inside the affinity.conf, we can do cat of the affinity.conf. We see that for the interfaces it is default after, and we didn't change anything. So let's just reboot. And let's wait for the firewall to come back from reboot. So gateway number 1 is back from the reboot. We can log in. Log in and let's immediately check if we have correct affinities. We still have the configured affinities, and what's more important, change of the interface affinities does not change the cluster state. We are standby active despite of the fact that affinities indeed are different. Here we have CPU all. Here we have only certain CPU assigned. Let's now bring the configuration to the same, and we will do sim affinity -s for Ethernet 0 goes 0, Ethernet 1 goes 0, for the sync interface goes 1. And now we have the same configuration on both firewalls. Okay, all good. The next step would be just to bring the cluster to the same state of it was before, with the gateway number 1 as an active firewall. For this we will do CoreXL failover. It is CoreXL admin down. Now it is active, the other one is down, and CoreXL admin up. Now it is active, standby, how it should be. Let's review the changes that we done during today's lab. We have 3 interfaces on our firewall: Ethernet 0, Ethernet 1, and we have also Ethernet 2. And in the firewall, we have CPU 0, CPU 1, CPU 2, and CPU 3. These two CPUs are SND, and this is firewall workers and different firewall daemons. These two interfaces go to CPU 0, and this one interface go to CPU number 1, and then SND can distribute the load between firewall workers, and firewall workers can occupy either CPU 2 or CPU 3. Any firewall daemon also can occupy CPU 2 and CPU 3. This creates a clear separation between security network dispatcher functions and firewall kernel functions and firewall processes. This will avoid any delay for CPU time related to handling traffic from interfaces, and CPU time related to processing this traffic through the rule-based and security inspections. Today we reviewed CoreXL. Also, we reconfigured number of firewall instances and SND instances on a checkpoint firewall. Thank you for watching.